What's up, hackers? In our last video, we went over the theory and basic practice of DLL hijacking. We even went as far as making our first DLL in the Rust programming language. In this video, we're going to take it one step further and weaponize this capability. We're going to learn how to hunt for hijackable DLLs, how to understand how to spoof those DLLs and write fake ones that will be your hijack target, and then finally, what kinds of payloads you might put into those DLLs once you know how to make them. Let's get started. You may recall from our last video that one of the ways that we look for hijackable DLLs is to use ProcMon or process monitor to watch a process as it starts up and loads all of the libraries that it will use during its run. And as we see those loads happen, we're looking for name not found events on those DLLs for any DLL that is being searched for in a directory that we, the attackers, control. If one of those directories is searched before the DLL is eventually found and loaded someplace else, or if it's never loaded at all, then we have the capability of hijacking that location, putting our DLL there, and having the program run our code rather than the intended code. And that's a great way to look for hijackable DLLs. But you don't necessarily want to run ProcMon on a system that you've already gained initial access onto. So there are a few other ways, like running the SharpUp tool, which is a .NET assembly you can run through many C2 programs like Cobalt Strike or Sliver. There is also a database of hijackable DLLs called HijackLibs. I love this site. It has a lot of great listings of hijackable DLLs that you may be able to find on the target that you are working on. The one that I want to talk about today, though, is MpClient.dll. This one's crazy to me. This is a DLL loaded by, I'm not kidding, Windows Defender. Windows Defender is in fact vulnerable to DLL hijacking. Well, parts of it are. There are two executables inside of the Windows Defender directory that load or try to load MpClient.dll. These two programs are MpCmdRun.exe, which is the command line management tool for Defender, and nissrv.exe. One of the reasons why this is so insidious is because in many cases you have to accept the Defender directory or Defender executables from Defender itself because it's going to be doing a lot of scanning. And you would expect Defender to be doing bizarre things, and so often it will slip past threat hunters. Let's watch the load of DLLs from these programs using ProcMon just to see what it looks like once we have a known target. Okay, for simplicity's sake, I have copied the two Defender binaries into a separate directory outside of Program Files, Windows Defender, but HijackLibs will tell you exactly where to find them if you want to do the same thing. And these commands will run outside of their local directory. So we have MpCmdRun.exe and we have nissrv.exe. I also have Process Monitor ready to go here with the three filters that we care about. The first one, of course, is process name is MpCmdRun. We'll do that one first. Then we'll do result is name not found because we're looking for anything that it couldn't load. And of course, the path ends with DLL. So there's our filter applied. We're capturing live. Let's go ahead and fire this off. And wonderfully, we actually get this error message saying the code execution cannot proceed because MpClient.dll was not found. Take a look at this. The first place that it looks, of course, is in the local directory. And as we go through all of the other folders, is it anywhere at all? No, it's not. Now, running ls on the directory where it originally should live does reveal that MpClient.dll is there. But because we can copy this binary anywhere on the system and then use it, it's going to look like a signed Microsoft program is running the DLL that we want it to run if we move that file anywhere else. This technique is also sometimes known as DLL sideloading rather than DLL hijacking because we're moving the binary into a place where we know we get to control the order of searched paths that we want. Now, if we think back to our original DLL hijacking example, we had our program called HijackMe invoke a function in the DLL called main. We knew that function and we examined it with Cutter to find out what function it was invoking from the DLL so that we could spoof it. We don't yet know what functions MpCmdRun or nissrv actually use inside the DLL. So the first thing we might try is to write a DLL that just uses DLLMain to do what we want. That may not work depending on how the DLL is used inside of the binary, but we can always give it a try. Here we have our evil DLL program that we wrote last time. As a quick review, we are importing these Windows dependencies from the Windows RS crate. We are writing our own extern-c function that we're exporting so that the DLL advertises or exports that function for other programs to use, called main. We could call it whatever we want. We just happen to call it main. And all this does is pop a message box that says DLL hijacked. That's all it does. We use the no mangle macro to make sure that the function name stays the same after compilation. And then we have the required DLLMain function, which is what makes a DLL a DLL. Right now, we're not doing anything inside of DLLMain except returning true. Because we don't know what functions yet that MpCmdRun or nistserv.exe use from MpClient.dll, we're going to attempt to use DLLMain just to see if it uses that default entry point and see if we get lucky. So we're just going to invoke the main function right here in DLLMain. And over in our terminal, we're going to run cargo build for release. And then I'm going to copy it into the same directory that my copied over Defender binaries are. So that will be the first place that the programs look for the DLL. It'll find a correctly named one, and then we'll see what happens. So I'm going to copy from my target x86-64 PC Windows GNU release evil DLL.dll. I'm going to send it to where my demos folder is on my F drive, DLL hijack /defender/MpClient.dll. This again is using Windows subsystem for Linux, so it's really easy for me to interact between the Windows side and the Linux side. Sure enough, there's MpClient.dll. Now let's fire off MpCmdRun and nistserv and just see if we get one of those message boxes. We don't, but we do get a hint. We get an error saying the procedure entry point MpQueryEngine config dword could not be located in the dynamic link library. Okay, so that happens, but DLLMain didn't happen. Let's try nistserv. This time we get the error message, the procedure entry point MpConfig close cannot be located in the dynamic link library. So we now know about two different functions that these libraries require, and we need to spoof them, at least those, in order for this to work. In order for us to understand all of the functions that we're going to need to spoof, and it's not that tough to do, out of MpClient.dll, we're once again going to use Cutter to examine these programs. Okay, I have MpCmdRun.exe loaded up in Cutter. It's a lot smaller than nistserv, also less weird. I, as a defender, see MpCmdRun executing on my systems all the time, so as an attacker, that would be the one I'd choose over nistserv.exe. So that's the one I'm going to focus on. We don't have to read any assembly for this part. We just need to look at imports. So as we go through the list of imports, we of course are looking for what it imports from MpClient.dll. There it is. So there's a pretty long list of functions that it imports. And if you remember, we did see MpQueryEngine config dword as one of the functions, the entry point, in fact, that failed when we tried to use just DLLMain. But because we don't know how these functions work together, the safest thing to do, honestly, is to spoof all of them. It's actually not hard. It's just a little bit of copy pasta. So first thing we want to do is get this list of functions, get it out of Cutter and into something more usable. Okay, so full disclosure, I totally forgot that you can't easily copy the function names out of Cutter. I just kind of default to it because it's my go-to tool. But luckily, there is another tool we have that will easily copy those things out. So sorry, we had to open up Cutter for no reason, but it's always good to get some practice using that tool. So instead, what we're going to do is use PEStudio, which will definitely let us get this data. So once PEStudio loads the MpCmdRun.exe, which, by the way, it looks malicious when you load it up in here, we're going to go to the imports section and go to the MpClient.dll listings, and we're just going to select all of the MpClient.dlls, right-click, copy import names, and let's head over to VS Code, and let's just make a new file quickly, and then just paste these in, because we have some work to do with this. Basically, what we want to do is, for each of these, create a new extern-c function, just like we did with main. But what we're going to do with each of those is add a no mangle, add a for one, and we're going to make it call our main function. So just a little bit of text editor wizardry here. So to start, I'm going to hit Control F and bring up my find and replace, and I'm going to enable regular expression mode by hitting this .star icon. So the first thing I'm going to do is replace the beginning of the line, which is the caret, with extern c fn space. That's it. So we're just going to replace all. Because the beginning of the line is different than the first character, we didn't actually mess with any of those things there. Now we're going to replace the end of the line, which is the $, and replace it with parentheses, doesn't take any arguments, curly brace, main, because that's the name of our evil function, curly brace. Okay, let's replace all. Now it looks like Rust, and in fact, VS Code even told us that it was Rust based on its syntax detection, even though we didn't save it as a Rust file. Lastly, we need to get that no mangle macro. So what we're going to do is we're going to take the beginning of every line, and we're going to replace it with no mangle and a new line. And that is our set of spoofed functions. We're going to take that, copy it over into lib.rs, wherever you like. And now we are going to remove the main invocation that we had in DLLMain. We don't need it anymore, but we are going to let these spoofed functions do our work for us. So we've saved this out. Let's go ahead and build it one more time with cargo build. We're once again going to copy it over, and then I'll just do this from PowerShell. Let's go into Defender, and let's run MpCmdRun.exe. And there's my pop-up. We have successfully hijacked the DLL. Note that we got it without any error messages. And that is how you spoof functions that are used by a program when it imports DLLs. Observe what it imports, then write shim functions that call your evil function inside of your Rust program, or any other language, but we're focusing on Rust today. Hey, if you liked that regular expressions trick that you just saw in Visual Studio Code, you can learn more about how to use regular expressions in VS Code and in Vim in our free course on Intro to Regular Expressions at taggartinstitute.org. The course is free, or there are optional $1, $5, and $10 purchase options, so you can pay what you wish if you feel like the content is worth it. Hope you enjoy the course. Now back to the video. Some of you may be asking, hey, if we saw that error message when we tried to run MpCmdRun with the DLL without these spoofed functions, without these shim functions, couldn't we just use that entry point and then just spoof that one? Wouldn't that be enough? I promise that I didn't just do all of this hard work to show off the regular expressions trick, although that was part of it. Sometimes just doing the entry point is enough, but sometimes it isn't. And let's demonstrate what happens when we try to do just that. So we saw in that error message that the entry point that we were told about at first was MpQuery engine config dword. Cool. Let us comment out every other function shim here. Let's rebuild and copy it back over. Now let's rerun MpCmdRun from Explorer. And now you can see we're getting a new error that mp_get_sample_chunk is missing. Okay, well then let's try to uncomment just that one. I think you can probably see where this is going. And now we have a new one. So because we don't really know exactly how the entry points are handled inside the DLL at this level, it's easiest to just take all of the imports and spoof all of them so that there's no questions about what actually needs to be spoofed. Yes, it's a little bit more copy pasta, but you have the guarantee that you're going to hit the functions that you need to hit. So it's definitely worth it. Once again, we're going to rebuild this thing to work and then fire this off against MpCmdRun. This time I did it, of course, from the PowerShell, but we do have a successful run. Okay, now that we have the theory of the shim functions out of the way, it's time to weaponize this thing and actually add some offensive capabilities to our malicious DLL. We're going to do that with process injection, which is a way of injecting our own shellcode into a running process, either the one that we're currently in, which is known as reflective injection, or another process that we can gain an access to, gain a handle to, that's called remote process injection. We're not going to go into the details exactly of how those work. We'll talk about the basics, but that's outside the scope of this video. We're focusing on DLLs. Now, why would we do all of this for DLL hijacking? And one of the reasons as red teamers is threat emulation. This article from Trend Micro talks about the Longzhi APT that in fact uses DLL hijacking with this very DLL, MpClient.dll. And so knowing how to move from that hijack to actual remote code execution is pretty valuable. And one of the most common things you're going to want to do is establish a command and control beacon so that we have initial access or persistence on the target. Now, I've written the Rust code to do process injection I don't know how many times, and frankly, I was getting a little tired of writing it. So for this video, I created a new library in Rust called Bolus that allows you to simply import this library and then use it with your shellcode formatted however you like in order to easily do remote or reflective process injection. And that's going to allow us to get up and running with our malicious DLL a lot faster. So we'll talk about Bolus usage, but inside of the Bolus source code, which of course is open source and on GitHub, you can see the steps that are necessary for process injection. Let's quickly take a look at the source code here, just so we understand what is taking place for this version of process injection. Okay, so process injection via Bolus, or really via the Windows API in Rust as a shorthand. The first thing that we need to do, whether we're doing reflective injection or remote injection, is grab a handle, which is a reference or a pointer to the process in memory. We do that using the open process Windows API function. We also have to specify the permissions that we want to open the process with and the process ID that we're trying to access. In our case, for remote injection, it would be a process ID that we know about, or if it is reflective injection, we would actually use another function called getCurrentProcess, which just returns the handle right away to the current process. No need to specify an ID. The next step, which is the same for either remote or reflective injection, is we have to allocate some memory space where our shellcode is going to go inside of the new process, inside of the process. We do that with virtual alloc x. And again, this is one technique for remote. And again, this is one technique for process injection, and it is one that is detectable by Windows Defender. I'm not talking about evasion right now. I'm simply talking about theory and technique. There are ways to do this that are a little bit lower level that will evade basic defenses. So that is something that I leave as an exercise for you. Once we've allocated the memory, and we do it with read-write permissions, importantly, so that we are not flagging on execution space just yet. We will make this memory executable, but not yet. Once the memory is allocated, we call write process memory to write our shellcode into this new space that we've allocated. So here's our process handle, the base address of our new space that we've just allocated, the shellcode that we're going to, a pointer to the shellcode that we're going to write into it. We then change the memory space's permissions from read-write to read-execute. This avoids the easy detection of looking for read-write-execute memory space, but it does allow us to execute the shellcode once it's been written. Then we kick this off with create remote thread, another easily detectable technique, but an important one to know about nonetheless. This kicks off a new thread inside the process using our new shellcode as the starting point for the memory space. Finally, we close the handle so that we don't have that floating around. We also have this wait for single object down here, which is important to use if the program that you're injecting into doesn't have a main loop. What this will basically do is keep the process open so that it doesn't close and you don't lose your beacon or your session. So all together now, open the process, allocate memory, write the memory, change the permissions, create remote thread. And I should mention that you can use create remote thread even when you're using reflective injection. All you do is just give the current process ID to create remote thread. And in fact, even under the hood, create thread is just an invocation of create remote thread. So the good news is that you don't have to reinvent the wheel here. I wrote Bolus so that we could do this easily in our DLL. To get started using Bolus in your development environment for your evil DLL, all you need to do is run cargo add bolus. That will add the Bolus dependency, which has been published to crates.io, to your environment. Once that's done, we're going to add the use bolus invocation to the top of our lib.rs for our evil DLL project. So we're going to use bolus, and then there are a few things that we need. The first is the load and inject functions. Those are top-level helpers that are going to make it much easier to work with the underlying injector and injector types. Then we need to get injectors, and then injection type and injector type. And yes, there is a difference. Injection type refers to remote or reflective, and injector type refers to whether we're going to use a URL-based source of shellcode, whether we're going to use an embedded source of shellcode, or we're going to use some other source, and there are opportunities to develop this further. Now, I really like using the C2 framework of Sliver. Its shellcode is gigantic, and so I like to host it on an HTTP server or something else like that my dropper will then call home to and then pull it in, rather than hosting all of those bytes local to my initial payload. So for our DLL here, we are going to use the URL injector type, and then we provide it the URL of where our shellcode is getting hosted. Let's head over to our attack box, our Kali Linux box, and set up all that shellcode from Sliver so everything's working as we expect. Okay, here I am in my Kali Linux box, which is, by the way, on the same network as my Windows machine that we're going to be targeting. If I run profiles, you can see that I have a bunch of profiles for like HijackLibs and things like that, but one of them I have, which is local, is this MTLS profile. Sliver has built-in support for communication over MTLS, which is encrypted out of the box, so I really, really like using it. You'll also notice that the format is shellcode. What I'm going to do then is do profiles generate -G to disable the Shikata Ganai encoding. This is Sliver inside baseball, but the Shikata Ganai encoding is supposed to obfuscate the shellcode, but mostly it just breaks the shellcode, so I always disable it. Save it as evil.bin and choose the profile name of MTLS and let that generate. Okay, and we're good. I'm going to just quickly open up another tmux window here and go to my payloads folder, which is where I'm running Sliver from. And if I ls, you're going to see a bunch of stuff, but one of the things is evil.bin. Fantastic. So I'm going to fire up a Python HTTP server on the same machine on port 8443. That way, I'll have a way to access this thing over HTTP. Let's head back over to Visual Studio Code and use this new URL inside of our injector. So I'm going to scroll all the way down to my main function. We're done with message box. And in fact, we're done with this unsafe block. Instead, we're going to use Bolus now for our shellcode injection. So we're going to start by defining our injector type, which is URL. So the way that this works is that we tell it the URL that we're downloading from, and we put that inside of the enum, which is URL. Let's see this in practice. Let injector type equal injector type : to get down into the enum, and you can see there's a URL right there. It expects a string, so we're going to give it a string. We're going to give it http : 192.168.1.114, which is my local IP address on 8443/evil.bin. Now you would want to obfuscate this more obviously in real life. Now this is not a string, capital S string. This is a string primitive, or stir, which we sometimes call it in Rust. So to make it a proper string, we use the .toString method. I know that's a little bit strange, that's some Rust inside baseball, but there is a difference between this data type and a capital S string data type. Now we can create an injector with the load function. We're going to load, and we give it our injector type. Easy enough. And you can see that that gives us a result of injector and then string. So we're going to quickly just unwrap that result. That's a bad idea in real programming practice, but we want to handle whether there was an error. But because we're just trying to practice with this, we're going to unwrap it to get our injector type. Notice that difference, by the way, if you have Rust Analyzer running. If I don't have that unwrap, our type is result, injector, and string. If we run that unwrap, Rust Analyzer is like, oh, okay, you want the underlying data, so we're going to assume that everything worked and you get yourself the injector. Now we can run inject, which takes an injector, and then an injection type. Now for this one, we can do this inline, or we can do it as another variable. In this case, let's just do injection type and then : reflect, because we're going to do reflective process injection. We'll do that first. And lastly, we need to tell it whether we want to wait for a single object or not. In our case, we do, so we're going to say true. Lastly, this returns a result that we have to handle. And so we're going to, again, just .unwrap this so that Rust Analyzer doesn't yell at us. Okay, our lib.rs is created. So now let's try to run this once we recompile it. We will build. This might take a little bit longer because now we're importing all of Bolus's dependencies, which includes a good chunk of the Windows API, as well as a few other things. Okay, if you follow this video exactly, you're going to get a warning from the compiler that we have unused imports. That's fine. Don't worry about that. It doesn't prevent the compilation. Once again, we're going to copy this over to MpClient.dll. I would make sure that Defender is off because, again, we are not trying to do any evasion right now. And let's fire off MpCmdRun.exe. But before we do that, let's make sure that our MTLS listener is up and running. Everything looks good. Sliver is ready and waiting for a session. So let's go ahead and fire off MpCmdRun.exe. And there's our session. We use for who am I? Cool. And let's, of course, pop some calc. You'd love to see it. All right, there is our successful reflective injection into MpCmdRun.exe. So we've moved from DLL hijacking to process injection. Just to show off a little bit of Bolus's capabilities, if you wanted to do something a little bit more interesting like remote injection, you can absolutely do that. Back in our source code, let's change this to remote, and you'll notice that remote takes a string as well. In fact, let's clean this up a little bit. So we're going to just clean all of this up and say up here, let injection type equal injection type remote. And just like we did with the URL, we're going to give it a string here. In this case, we give it notepad.exe, and it could be any process name that you have permission to access as the user that you're going to be running as. Okay, that looks good. And we're going to use injection type as our second argument to this function. That looks good. Let's recompile the code, copy it back over. And of course, to make this work, we need a running instance of Notepad. So let's get that going. Now let's fire off MpCmdRun.exe one more time. There's our session. If we use that session, if we run PS for the process list and continue through it, we will eventually see a green listing, which is the process we're currently in, and there is my process I'm running inside of notepad.exe. So remote process injection was successful. Okay, that about does it for DLL hijacking and process injection using Rust. If you liked this video and you like what we're doing here, I'd love for you to consider checking out some of the courses at taggartinstitute.org. We're creating free or accessible cybersecurity and technology educational content for all people, just like this. And if you'd like to support our mission, we'd love for you to consider a purchase of one of the courses for $1, $5, $10, or $15 for the advanced courses. Thank you so much for watching. I hope you enjoyed it. Happy hacking. Be good to yourselves and be good to each other. See you next time.